Good morning, everyone, and welcome to the webinar. I am Natasha Abrahams. I'm the Strategy and Government Relations Manager here at the Australian Academy of Technological Sciences and Engineering, or ATSE. I'd like to begin the session by acknowledging the traditional owners of the lands from where I'm joining today. For me, that's the Wurundjeri people down in Melbourne, and I pay my respects to their elders past and present. I would like to extend that respect to any Aboriginal or Torres Strait Islander people joining us today, as well as to acknowledge the traditional owners of whatever country you are joining us from today. Before we go on to today's webinar, I do want to start with a bit of housekeeping. So first, I'd like to remind all attendees that they have agreed to abide by ATSE's Code of Conduct, including as you enter your questions into the Q&A channel. This webinar will be recorded and the recording will be made available on ATSE's YouTube channel shortly after today's session. And we have captions enabled, so if you do need them, you'll be able to get them popped up at the bottom of your screen. As the session progresses, we will have some feedback surveys, and we would really appreciate if you complete them later in the session. And we are really keen for this to be as interactive as possible, so please do be sure to submit your questions in the Q&A box at the bottom of the screen at any point throughout the webinar for our wonderful speakers. So before I do hand over to our moderator and our panelists, I just thought I'd share a little bit about myself. So I've been working in science policy at ATSE for 3 years, and prior to that, I was in higher education policy. I completed my PhD in sociology at Monash University in 2019, and my research focused on mass media communication of science. I also had the privilege of studying social sciences and astrophysics in my undergraduate degrees. So this dual focus really taught me the value of different ways of looking at the world, whether that's through equations or through human behavior. And I love being able to use these skills and knowledge every single day as I work on science and evidence to inform policy outcomes. So this wonderful webinar series is brought to you by ATSE's National STEM Education Initiative called STELR, which is designed to engage young people in rich STEM learning at school by using hands-on and curriculum-aligned resources to explore the principles of sustainability and renewable energy. We have over 280 lessons and over 100 hands-on activities for use in the classroom. You can find out more on our website, STELR, STELR.org.au. The theme for today's webinar is Quantum Leap, Science and Tech Careers on the Cutting Edge. It's an exciting chance for us to help you explore the many pathways and career opportunities available for students in quantum technologies. And we have some really incredible panelists joining us today to do just that. So with that, it is my pleasure to introduce you to our first speaker, Australia's former Chief Scientist, as well as ATSE Fellow, Dr. Cathy Foley, AO, PSM, FTSE. A little bit about Cathy, but I will leave it to Cathy to fill in all of the details. She was our ninth Chief Scientist, Australia's ninth Chief Scientist from January 2021 until the end of 2024. Prior to this, Dr. Foley had a long career at Australia's National Science Agency, CSIRO, including as their Chief Scientist. Dr. Foley is an internationally recognised physicist with major research achievements in superconductors and sensors. Dr. Foley's scientific excellence and influential leadership have been recognised with numerous awards and fellowships, an Order of Australia for service to research science and to the advancement of women in physics. She is an ATSE Fellow elected in 2008, and she is an inspiration to women in STEM across the globe with her tireless championship for equality and diversity in the STEM sector. So with that, Cathy, thank you very much for joining us today and for hosting the webinar and taking part in celebrating the International Year of Quantum Science and Technology with us. Over to you.
Hi, everyone, and thanks, Natasha. It's so good to be here. And this is one of the areas which I really love doing when I've been in my career all the way through it. So first of all, before I start telling you about my career, I thought I'd just quickly mention that I'm going to be joined by Lucy Daldig and Will Campbell, and they'll be telling us about their careers so far as well. So, and I'll introduce them more too as we get closer to their moment. So maybe we could start by showing the first slide. And I thought it'd be really good to point out that when I was in school, I actually came from a family where science really wasn't a big deal. But I was always curious about the world around me. And I loved science and loved asking questions. I have to say, though, that when I was in year 8, I was actually just this morning looking at some old memorabilia, looking for something, and found my year 8 report card, which was not a pretty sight. I definitely decided that school wasn't for me at that time in my life. But eventually, by the time I got to year 10, I had some amazing teachers and really started to excel in maths and science, particularly physics and maths. And you can see here, there's a picture from my final year, the final yearbook, where you can see that I was planning to be a high school maths and science teacher, because that, for me, that was the pathway. Women at that stage usually were teachers. This is in the 1970s. I finished school in 75. So being a teacher, a nurse, a nun, because I went to a Catholic school, a secretary, get married, not have a career. So these were things which were really the offering. So the idea of a scientist was something more that Einstein's cousin would be doing, certainly not me. But I also had, because of my schooling, a really deep social justice value. And so when I finished high school, I actually worked with the Mother Teresa nuns in Burke. Now in 75, our treatment and support of Indigenous people in Australia was woeful. And that's a picture of me with some of the kids who were in my childcare centre I set up for the time I was working there. That was a little preschool, and kids just came in and had a chance to just have some games and play. But it opened up for me something which was an important value, which has been deep within me ever since. And that was that I learnt at that time that when you have something where I could see an injustice or something where the system wasn't working, I didn't want to be the person who's working on the one-to-one, which is very important, that frontline worker. I actually wanted to get in there and change the system. And I think that's sort of been something that's been throughout my career. And if you go to the next slide, I went through and you can see there, that's me when I was a primary school kid. I was dyslexic, still am. When I'm really tired, words just move around on the page for me. And it was something where I was seen as someone who probably wouldn't amount to very much. But I always had that curiosity about me, painting the walls with Vegemite to see what that would look like, riding my bike with my eyes closed, or my scooter with my eyes closed when I was about 4 years old, and running into the clothesline and breaking my arm, trying out different things with nature. I love collecting leaves and dirt and things like that. So science was an obvious thing, but there was no clear pathway, but school opened that up to me. So I went to university at Macquarie and I did a science degree. I didn't know where I was going to major, but physics attracted me and always had done. I loved it at school, but I didn't think I was smart enough. But the social situation at Macquarie Uni, where they really made me feel welcome, which back then there weren't too many girls in physics, led me to actually major in physics. I was going to be a school teacher, as I mentioned before, but when I'd finished my DipEd, the diploma in education, which you do after a bachelor's degree back then to be a teacher, I ran into my biology lecturer from when I did biology in first year at university, Heather Adamson, and she changed my world because she said, "What are you doing next?" And I said, "I'm going to be a school teacher." And she said, "Oh no, you were so good in the lab. You should do an honours year. I know you'll get first class honours, you'll win a scholarship, and you'll go on to be an amazing scientist." And I did that because she encouraged me. And it was that chance interaction in the car park at Macquarie University on a late Friday night, actually, that changed my career pathway. So I did a PhD at Macquarie University, and I applied for jobs in the newspapers because back in 1984, that's what you did. And then in 1985, I started at CSIRO at the West Linfield laboratory there. And 36 years later, I ended up becoming Australia's chief scientist. So if you press the button there, yep, I still can't believe that that happened. And I had the most amazing 4 years doing that. But while I did it, I also managed to have a family. So I have a blended family of 6 kids, 3 of my own and 3 stepchildren. And you can see my daughter there. And if you press the button again, you can see years later, my daughter had her own child last year. So I'm a granny now. So if you go to the next slide, my career was one which is working on solid state physics, which really is a version of quantum. So I worked on superconductivity at CSIRO, and when I was at Macquarie University, I worked on semiconductors, working on what was a new material then called indium nitride. In 1986, thereabouts, there was a discovery of what was called high temperature superconductors. And these are materials which, if you cool them down, the resistance to the flow of electricity goes to zero. And I was able to be part of a team that worked out how to make thin layers of this material. It's made of yttrium, barium, copper, and oxygen, which is really hard to make quality material. And then I made a structure, which you can see there in the middle slide at the top. It's there's a 20 nanometer bar on that transmission electron micrograph that shows a grain boundary, or it's got their GBR. And that grain boundary was able to create a structure, which is about a nanometer or so wide, that when an electric current goes across it, it creates the ability to interact with magnetic fields. So that then if you put that into a device, you can make a sensor called a superconducting quantum interference device that is able to detect very small magnetic fields. And so I went all the way through from working out how to make this material to making devices to being able to make systems. And at the bottom there on the left-hand side is a system called LANTEM, which was commercialized. And that's able to find deeply buried ore bodies in about a kilometer underground, and has been commercialized. There's about 13 of them around the world. They're used, they have a life of their own. It's a little bit like looking at your children, looking them up on Instagram or Facebook to see what they're up to. I look at the Australian Stock Exchange to see if anyone's made an announcement where they've used LANTEM to discover a new mineral deposit. It's discovered multiple billions of dollars of mineral deposits. Some have been realised, some not. We've also flown it in the air. If you look at the right-hand side, we've put that SQUID system, or superconducting quantum interference device system, into an airborne system. And you can see there we were doing field trials with it dangling under a helicopter. But also with that in the middle was the importance of publishing your work. And I've been involved with scientific publishing, and the journal Superconductor Science and Technology is a journal which I publish in a lot. And it's actually, you can see my work is on the front cover. But since then, I've become the editor-in-chief of that journal and have been for about 10 years. So that was sort of my research background. And I had lots of different roles in CSIRO, including over time lifting up to being someone who was looking more at the way science is done and organizing it to enable others to do it well. And if you go to the next slide, I want to use that just to give you a brief idea of what it was to be Australia's chief scientist. My role, it's appointed by the Prime Minister, and you can see me there with a meeting with Prime Minister Albanese and the National Science and Technology Council. And my role was to provide evidence-based advice to government so that they were able to make the best possible decisions with the best evidence and information. And luckily, since I clearly don't know everything, I was able to reach out to the whole of the Australian research community, and they always dropped everything to help me with that. And so another thing which was important for me to do was to champion Australian science here and overseas. And so this is something which is easy to do because Australia does amazing research. And the other one is also to see how I can make the research system as impactful and effective and efficient as possible. And so there was lots of different things that I did during that time. But one of my favorite ones was engaging with chief scientists from other countries. And there's a picture there of, for a short time, the Five Eyes, that's USA, New Zealand, UK, Australia, Canada, had all women chief scientists. So that picture there in the middle is a rare moment in history where we got together in Ottawa last year and had a meeting, and we used to meet regularly and share information and intel. And probably one of the biggest things I did as Australia's chief scientist was to actually assist the government in developing a national quantum strategy. Australia has amazing research, and it's something which is really important to be able to turn that research. And we've invested billions of dollars and have got critical mass and a whole lot of people who've graduated from the university sector in able to take that great research, spin out companies. There's about 40 companies that are quantum-based companies in Australia, and turn that into a new industry for the country. We've never done that before, of hardware, big fundamental science turning into something which is going to be part of our everyday. So for me, it's been a great honour to have been part of that. And that's why I'm so excited by hearing from our generation coming through today. And so if we kill the slides, I want to introduce our next speaker. So our next speaker is, I'll just get my notes here, is Dr. Will Campbell, and he's a research associate in experimental physics at the University of Western Australia. Now, he completed his honours degree in physics as well as his PhD in quantum technologies and dark matter research lab, well, at the quantum matter and dark matter research labs at University of Western Australia. Now, he specialises in the study and application of hybrid quantum acoustic systems for fundamental physics, because this all our quantum stuff starts at that fundamental level. So, as well as pure scientific research, Will's interests also lie in the education of quantum physics in schools and increasing the general uptake of STEM-based careers. So we've got a lot in common there. So over to you, Will. I'm really keen to hear about your career pathway.
Thanks so much, Cathy, and thanks to ATSI for having me. Really happy to be here in such a wonderful and exciting panel. So I was tasked to throw up some images describing my pathway into physics, and so I liked. When I generally get asked to do this, I like to put up a bit of a different kind of story. And some of the most amazing things that have happened over my life, funnily enough, haven't had much to do with physics, but physics is what got me on this journey. So I really like to highlight this because one of the questions that I faced coming through my journey is how did I know, or when did I kind of know that a career in physics would be right for me? In a couple of echoes and shades, I guess, with Cathy's amazing stories, I really didn't think I would end up as a researcher, or certainly a doctor in science of physics at all. I went to an art school and did drama in high school, which I really loved, and at times was probably more of a troubling student for most of my wonderful teachers that got me through. But the key point is I always really did have an interest in physics. That doesn't mean I was necessarily good at it. And I think some of my early marks would really reflect that. But I was really interested. So I think that if you're a high school student or an early university student and you have an interest, I think that's enough to know that a career in physics is something you should seriously consider. Because the longer I went on, I wanted to be an engineer at the start, and the sentiment around that time was that engineering can make you a lot of money, which I don't disagree with. And being an engineer would be a fantastic career. I don't want to knock that, but certainly a career in pure academia and pure science was a bit more convoluted, I think, and not very well communicated as to what that would look like. So for me, knowing when it was right, like it's really easy to answer retrospectively because I never really knew whether it was right for me until I got to university. And the wonderful thing about Australian universities is we're so blessed that they provide you great options and tools for you to figure out whether a career in academia and science and scientific research is right for you, because it is quite a different job day to day than what you would be doing in industry and stuff like this. So when I got to about the point where I decided to choose an honors in physics versus a master's in engineering, this is when I started being presented with a work life that kind of looked like a career in research, and I really enjoyed it. And so I like to put these photos up there of me acting in high school, or me playing, coaching a football team to a premiership and playing music, as well as some of the highlights of my career, which, and there's been some great highlights. I've been to some wonderful workshops. I got to visit the Large Hadron Collider at CERN in Geneva, and do all these wonderful things. But I think the point I really want to make is that there is no one fits all kind of type person that becomes a career academic or a career physicist. I think it really is for everyone, and especially people with diverse interests. As long as you find it interesting, the longer you go on and follow that journey, and the more I listened to that, I liked my physics units better than my engineering units. I liked the people that I met in physics a lot. As long as you keep listening to that and listening to yourself, the more doors will open for you, I think. And that's really something that I'm very passionate about and like to communicate as much as I can. So that's kind of my story. And so I hope you can find a takeaway from it.
That's great. Thanks, Will. There's already questions popping up where people want to know a bit more. So let's come and meet our next speaker, who is Lucy. Now, I'm just pulling up my Lucy slides. So Lucy is currently pursuing her PhD in quantum materials. And she's specifically looking at topological photonic crystal semiconductor lasers. And I find that fascinating because that's sort of what I wanted to do, but it was way too early in the creation of physics to be able to get there. So I'm sort of slightly envious that she's working at the end, which I never got to. She completed a Bachelor of Science with honours in high performance computational physics at the University of Adelaide last year. And she majored in theoretical physics, but she jumped ship to experimental physics, completing her honours research on radar studies of Adelaide's microbats with the Space and Atmospheric Physics Research Group. But now she's working on quantum materials and devices under the guidance and supervision of Professor Glenn Solomon. So, Lucy, over to you. I'm really keen to hear more about how you got there and how it's going.
Thanks, Cathy, and hello from Ghana country. I just want to briefly acknowledge that, I have the privilege to live and work on Ghana country, and I want to extend my acknowledgement to the elders, past and present. So kind of as a reflection, I suppose, of the story so far, my journey into quantum physics didn't make a lot of sense going forward, but it makes a lot of sense in hindsight looking back at it. So I graduated high school back in 2013. I took maths and English, chemistry and physics, and it was all with the aim of getting into medicine. So I was really hooked on medicine from an early age, but I think it was more because it was the first exposure I had to seeing a scientist, I suppose, in the real world, or someone applying science in the real world. And once I got into medicine, I realized that it wasn't quite what I was looking for. I didn't want to be the one, kind of similar to what Cathy was saying, I didn't want to be the one applying medicine day to day. I kind of wanted to look at the more systems and science approach, the backing of medicine, I suppose. So I tried biomedicine and then I tried public health with maths and computer science, and it all wasn't quite sitting quite right with me at the time. I think just university, it wasn't the right time for me to go to university, and I ended up working instead. So I worked for a while. I'd actually set up my life over on Kangaroo Island with my partner and was, yeah, pretty happy over there. But I realized, I had the luxury of being bored, that I wasn't intellectually stimulated enough, and made the decision to come back to uni. Um, so this time around, I chose to study high performance computational physics, which admittedly at the time I thought was going to be the physics of computing. So I really wanted to know how those ones and zeros that people talk about actuated in real life. How are they physically represented? But it turns out my degree was how to compute physics, the computing of physics. But it was a really happy accident. Fell in love with physics and maybe went through a few different phases throughout my university degree. I think it really started with understanding the difficulty of computing mathematics. So I really fell in love with computing and mathematical computing. I took a few electives in that area and I thought, oh, this is it. I'm going to do my PhD at the Australian Institute of Machine Learning, which is just down the road. And then I went through the space phase. So I went to a space hackathon and really fell in love with the space industry here, and all the events that are happening in that area. And I guess took a lot of electives in astrophysics and really fell in love with that area. And I haven't fallen out of love with it, but then I guess the next phase I had was earth sciences. So I had a few friends who were doing their research degrees. And I spent a lot of time hanging out in their offices, and was lucky enough to do some summer research projects over in earth sciences, doing some computing some coding for them for their research. And I thought, oh, this is a really cool opportunity to apply what I've learned in physics to earth sciences. And I think that's probably what led me to take on the honours topic that I did. So it was still under the physics bubble, but yeah, it was using weather radars to study Adelaide's microbats. So we had this strange signal return that looked like rain, but it turns out that it was these tiny little microbats that were flying up to 3 kilometers. So at these incredible heights that no one's actually been able to verify that they were at these heights before. So that was some really interesting left of field research, I suppose. Um, and then our honours year at Adelaide Uni, at least, is almost like a year-long job interview, a two-way job interview, where you get to take subjects and really hone in on what area of physics that you can see yourself in and that you really enjoy. And your lecturers and professors get an idea of how you work and how you think and where you might fit within their research group. And during that year, I took topics in quantum materials, which is the study of these materials that have these behaviors that can't be explained by classical physics. They're these like purely quantum behaviors. And I found that really enticing to think that we could uh, not just study quantum mechanics theoretically, but see how these strange behaviors actually played out in the real world and design useful devices based on that quantum physics. So yeah, I really fell in love with that area, and I also finally got to learn about the transistor and how those ones and zeros play out in the real world. So I was hooked, and yeah, that's how I ended up in quantum materials. So I'm only a couple of months into my PhD now, and basically using photonic crystals to make uh, high quality, high power lasers. And yeah, photonic crystals, I guess, are similar to how you might see butterfly wings that reflect only a certain color of light. So that's kind of the real world analogy, I suppose, that I'd use. And yeah, so that's where I'm at today.
There we go. Sorry. Thanks. Thanks so much for that, Lucy. I just want to remind everyone that you need to put your questions in the question and answer section on the bottom of the Zoom call, and we'll work our way through that. But let's kick off with a question first for Will. You mentioned that that you start off with a sort of more arts and acting type direction. But when was the point when you really did decide that physics was for you? You mentioned there was, but you didn't actually say what it was and what was the influence that made that happen.
Yeah, so it was twofold. I touched on this, but I probably didn't get a chance to explain it properly. But over year 11 and 12, I wanted to be an engineer. So I always had that interest in STEM, I guess, in technology. Even from really, really young, I was obsessed with machinery, and like probably most young boys watching Bob the Builder and stuff. Like I think it honestly started all the way back there. But yeah, so I wanted to be an engineer. And so I was taking physics units, I was taking chemistry units, I was taking maths units. But the longer I went with engineering, the more I always gravitated towards physics, but I never really considered, or no one really communicated to me that a career in just pure physics research would be a good idea. I don't think, and this is through no fault of like any, I think I've had wonderful teachers that I'm still in contact with today that were so great. I think it's just one of those things where it is a little bit unknown. There's not that
So you
many.
sort of drifted into it?
Yeah, yeah, yeah.
Yeah. So that's really
Um,
great. You didn't have an aha moment like I did. It's
no, there was never a big revelation, but it was more a slow gravitation. Even in university, I did engineering all the way up to my third year, and physics was my second major.
mm.
So it was really just this little thing that was always on the side, and then slowly became larger and larger until I eventually made the switch, and
Oh,
I've loved it ever
brilliant.
since. Yeah.
Yeah, that's great. Lucy, I was really interested in your career pathway. Now, when you're looking back, is there anything you've learned that you think, wow, I would have done things differently?
Yeah, I've got some very practical advice, I guess, is I would say stick out a semester. Like if you are at uni and it doesn't feel quite right and oh, actually I want to do this thing, it's worth kind of seeing through a semester and a checkpoint because you can always use those credits later and you don't know how yeah, if I'd stuck with some of those maths and computer science subjects I'd done earlier, I could have used them later. So you really don't know how things are going to pan out. So that's one. And my friend told me I had to give the advice of always sit your SUPs. So if you get offered a supplementary exam because you didn't quite make it through the semester, definitely sit it. It's worth doing it. It can save
Oh,
you,
wow.
yeah, a whole semester of your degree. So yeah,
Not to
those are a
mention the
couple
whole
of,
HEX fees.
yeah, exactly. So
So
those are a couple of
that's
practical
really
tips.
interesting. It's not exactly the same, but when I went back to work after having kids, back then there wasn't an awful lot of maternity leave and childcare. So I went back to work with my children were only 12 weeks old. And I can still remember my stepmother telling me, and I was sort of saying, oh, I don't know, I want to do this. And she said, give it 6 months. And if you still
Mm,
feel that way after 6 months, then yes, you need to do what you need to do, but give it 6 months. And I really am grateful for that advice, because one of the tricky things would have been back in my time was that when you leave the research, it's very hard to get back in. I think it's a lot easier now. It's not perfect, but that 6 month rule, I think we should all
mm.
tattoo that in our minds. So that's a great one. So look, well, you mentioned, like me, that you weren't necessarily a top student all the time. So did your early marks in physics actually have any impact on your progression in your career?
Yes and no. I think Marx is a funny one. I think what I probably want to say first is you should remember that people have bad days. So I think one test doesn't make or break a career at all. My marks weren't really indicative that I would be a physicist. I don't think necessarily they weren't terrible, But to put it in, in university, for example, I can remember in my second year I got 55% in a maths unit, just scraped through, and really thought if I failed that and had to go back, I think I would have at the time probably thought maybe this isn't for me, But and then you can also say like, one unit doesn't make or break a career either, So yeah, everyone should be. I always tried really hard to get the best marks I could, and I think I was really good at studying, and I learned my own way of studying and what works for me pretty early on, which really helped. But no, I don't think my marks were ever indicative of whether I was going to end up in a career or not. Everyone gets bad marks, so it's just something. If you find interest in the subject and you get bad marks and you think, oh, I'm a little bit disappointed, but I like the material and I'm going to work harder on the next one. I think that's what it's all about.
No, I think that's really important. I mean, yeah, you look at my academic record and it's not one you'd pin up as stellar, but you are stellar at some things, and that's what I found was really important, is to focus on the things that you are really good at. So experimental work, my area, and also pulling together different bits of information so that you're able to really get cohesive understanding of something, so that you're able to see different bits of data or different experiments, and you can sort of see how they fit together to give you a step up. And just learning stuff and repeating it in exams isn't necessarily what science is all about. And quite often, I've actually seen people who haven't necessarily had stellar marks be brilliant physicists, because quite often it's the other things around that really lift up your ability to make progress on that. I don't know, Lucy, did you want to add anything to that?
Yeah, I think I've really found that I did really well at school, and then I found uni difficult. And I think throughout my undergrad, I definitely didn't get the best grades. And then I think honors, I really put everything into it to make
Me
sure I
too.
could kind
Yeah,
of,
it's amazing when
yeah,
you're focused.
yeah,
Suddenly, out of the blue, here came a first class honours, which got me a
yeah,
scholarship. Yeah, yeah.
yeah,
Yeah, I think
yeah,
motivation is really important, isn't it? And it's amazing when you're really focused on something, you really want something, and you know what you're doing. That's when it all comes together. That's what happened to me. When you've got too many opportunities and you think, oh gosh, you tend to thin out your efforts, and so therefore you don't
yeah.
necessarily deliver in the same way. Okay, look, let's there's a quick question here about what was the coolest thing I did as Australia's chief scientist. Probably the coolest thing was undertaking a national conversation on behalf of the government, asking the question, what is the science and research we need to do for Australia to be the country we want it to be? And that was amazing. I talked to people around the country, from school kids through to heads of industry, an awful lot of Indigenous roundtables, and we ended up with the national science and research priorities, which 5, basically, we want to be a prosperous nation. How do we do that and go to zero emissions? We want to be a healthy nation, but how can we do that when half the population has got chronic illness? So equal access, equal access to health and medical stuff, but also from a wellness perspective, dealing with mental health and aging and things like that. Elevating Indigenous knowledge and knowledge systems, which are really proud to do that. And thank you, Lucy, for re-acknowledging we should have done that at the beginning, because I think it's really important to make sure we elevate a traditional owners' knowledge and knowledge systems. Really different to our experience of it, but so much to add. Then the next one was, how do we do all this and have the nature that we want, so that we have our environment that is healthy when we take all our wealth and our livelihoods from the earth. So how can we have that tension, have our cake and eat it too? And then the final one, which I thought was really interesting, was how can we have a secure nation, not in terms of defense, but with mis and disinformation. You're sort of seeing this maelstrom coming on now where the world is really tricky. So how can we have water security, food security, make sure that people have lifelong learning and are curious, and being able to really have that security in our culture, so that we are maintaining our values as a nation, which I found was interesting. Everyone loved Australian values of fair go and that sort of thing, but also do that with all the stuff that's going on now and maintain our liberal democracy. So that was amazing. It was an amazing experience. Anyway, enough of that. Let's go on to the next thing. Here's a good one. Lots of change in physics over the years, particularly in technology. What do you think will be the most exciting areas or topics in quantum in the future? Lucy, do you want to kick off with that?
Oh. Well, recently I've been looking into the Microsoft announcement into their new type of quantum computing, or their new approach to quantum computing, these Majorana states. And I think that's been really interesting. I think just in general, there's always something maybe that seems new, but builds on like many, many years of research. And kind of like Cathy said, with the lasers that I'm getting to look into and create today, I wouldn't be able to do that if there hadn't been all the research leading up to this point. So there's always, yeah, something new and exciting, and you might not know what it is when you start your degree, but you'll sort of find your way there, I guess. You'll sniff out the path.
No,
Yeah.
and you should actually we should get those listening to look up the Majorana fermions. I can never say it
Mm,
properly. Amazing social history as well,
mm.
about a guy who vanished, came up with this thing, and it's taken decades to be able to get to a point where you can show that they exist. So I think it's homework for everyone. Will, how about you? What do you think future topics?
Yeah, I think it's very telling that we're in the year of quantum, and there's quantum strategies, and we're all from a background of quantum technology. You'd be amiss to say, that there's nothing left for you to do in quantum, which is probably the most contrary thing you could ever believe. There's still the jury's not out on the best architecture of qubit, which I think is a great point that people should pick up. Is that we still don't know the best path to quantum computing just yet. There's so many different ideas out there, like this Microsoft Majorana qubit structure, but other people have other ideas in Australia as well. And so there's so much to do in this field, and lots of fundamental questions to answer as well. Why is it that these qubits behave the way they do? So I think this is a really exciting field, and one that Australia is actually very good at. And has a lot of rich history behind. So, I mean, these are the kind of questions that hopefully our listeners and viewers will be answering for us one
Yeah.
day.
So one of the things is really interesting is so often through my career, people said there's no jobs in physics. What do you think is the case now? Because you're both early career, both in the university sector, but as you said, we've got a critical mass there. So what do you think is
Could not
different
be more
now?
untrue, I think.
What's that, sorry?
Could not be more untrue. I think there's so many opportunities in physics at the moment. You just have to get through that tricky part, which is the honors and the PhD, and it can seem like a lengthy commitment at times, I think. But for me personally, one of the reasons I'm so passionate about communicating this is because I'm probably someone who thought too hard about, is there going to be a job for me at the end of university? And in the end, listening to my passion, which was physics, opened so many doors. I think there are so many great opportunities for a career in quantum physics alone. And that's just my experience, so.
What about you, Lucy?
Yeah, I guess I'm just on the start of the journey yet, like not having to look for jobs yet, but certainly so far I haven't found any resistance for opportunities. Definitely all the steps along the way, and yeah, research projects that I wouldn't have even been able to dream up myself. So yeah.
No, that's true. With the burgeoning startup community and quantum industry, we're seeing people doing their PhD, either spinning out a company or going and working in companies, as well as taking postdocs in the university sector. So we can't get enough people to fill all the jobs that are there. There's a really important question here from our class of Year 7 students, and they want us to explain quantum physics for Year 7 students. Well, we'll start with you since this is your passion.
Sure. Yeah, so not an easy challenge, but I think before I answer it, it should be declared that the definition of quantum physics is something that I probably argue about with my colleagues that are quantum physicists. So if you're struggling to come to grasp with it, you're not alone. The way I would like to explain it, I guess, is the physics. It can start with the physics of the very small. Um, but this can be a bit of a misleading explanation because you can have very large systems that are quantum systems. So really, it's the physics of things at low energy scales and how they interact fundamentally. And what you'll kind of find is that when you go down to a particle level, everything looks really different, and the equations that kind of govern what we know about objects and they look very different and they behave very different. And so then you can go one step further and say, okay, that's great. You know, that's quantum physics. What's quantum technology? And this is kind of why we're all researching, I guess, is how do we harness that weirdness and these different kind of equations and these different ways that particles interact? How can we make that useful and scale that up? So I don't like the answer that it's the physics of the small or just the subatomic because it's not strictly correct. But
It's
yeah,
a
it's a
subsection.
start.
Yeah. Lucy, do you want to add any more to that?
Oh, maybe maybe an analogy. If you look at your computer screen and you see a nice image that you're familiar with, and then if you zoom in and zoom in and zoom in and zoom in, you'll see just a like a red and a green and a blue dot, or whatever your screen works. And that might seem really strange and abstract. How do you get those three dots to make up the full colorful picture that you're looking at? And maybe that's an analogy
That's
for
a
the
great one
classical.
too.
Yeah.
Yes. So, and I'll just add one other thing, and that is that we've got to remember that we've had quantum stuff for a long time. We started off, as Lucy said, wanting to understand how ones and zeros happen in computers. And that's because of what we call the first quantum revolution, where we were able to basically get materials like I was working on, those pictures I showed, and we were able to make structures in those materials at the macroscopic scale. That means a big scale. And therefore be able to control the flow of electricity or electrons so that we could make transistors. And then we were able to make better transistors and got to the point now we have zillions of transistors on a single chip. And we've got high performance computing we have today. AI, all those sorts of things that are part of our everyday. There was also another parallel with that, and that was the development of the laser. Originally, it was gaseous lasers, and again, being able to control light and photons. Light's made up of photons, and being able to control those so that and lasers are part of our everyday now. What happened around 2000, I guess, was what you might have heard of nanotechnology, which was all the rage back then. And what that just meant was that we created tools which could go, as Lucy said, into those macroscopic or microscopic points where we began to be able to see and control matter at an even smaller level. That opened up the door for things like different physics properties that we can really only understand by thinking of physics in a different way. So instead of it being that classical approach where it's almost like Newton's laws, where you push something and it moves, it actually get to a point where it's all about, this is going to sound really weird, but all about statistics and probability. And so the idea of saying, can we control that moment when things are in that space where we don't really know whether it's up or down, it's in that flipping a coin while the coin's in the air. Can we control that in a way? And that's what quantum is, the latest version of quantum is doing, is saying we're resting on the laurels of the past, building on that to be able to control matter at that way that allows us to do things we couldn't do before because we just didn't have the skills, but we're constantly building on those skills. And as a consequence, new abilities to do things, whether it's sensing, detect things we couldn't detect before, communicate in ways which are secure, so that we can't have any cyber attacks, or whether it's amazing computation that allows us to be able to do calculations in ways which are much. At the moment, we've got ones and zeros, but what if you had infinite ability to do calculations that we can, and then be able to solve problems we couldn't solve before? I don't know if that helps, but let's keep moving. So there's something says for people with more interests than they can reasonably pursue, how would you recommend sifting through them to figure out which ones to keep as hobbies and which ones to focus on in higher education? So, well, you sort of had to do that a bit when you were doing your acting and coaching. So, do you want to give this a stab first?
Yeah, I mean, that's a really tough one to answer, actually, because part of me wants to say that you can keep them all. I had some really fantastic advice from a drama teacher in high school when I was weighing this up. I don't think I was a phenomenal actor, so I don't think a career in acting was a serious consideration, but it was something I thought about. And one of my drama teachers told me that if I went to university and I did engineering, and she knew that I would like it. But eventually, if you starved yourself of creativity, it'd find its way back in your life naturally. And it really did. And so now I play a lot of music, and I do shows for friends and stuff, and I'm playing on the keyboard. And so that part of my life, I feel like that creativity just found its way back in a different form. So I think I wouldn't like to be encouraging people to sit down and think too hard about which hobbies they keep and which they remove. Just keep listening to yourself and doing what you enjoy, and don't worry about which one's going to be more important than the other. I think that's the really critical thing, is that if I thought too hard, I would consider engineering as the right option because there's more jobs and more opportunities, which was the truth on paper. But because I found physics more interesting, I paid more attention, and this is the cliche, but it really does work. So I hope that
Does
kind of
work.
answers it without answering it. But
Yeah. But we're running out of time. But I want to just ask one more question, which I thought is an important one, because we've been focusing on sort of traditional, living in capital cities. There's a question here that says, what opportunities would you like to see for students in rural and remote communities in relation to learning about quantum and pathways for future careers? Lucy, do you want to start off with that? It's a tricky one.
Yeah, it is a difficult one. Yeah, I lived on Kangaroo Island for a few years, and I know a lot of the students there had some opportunities, at least to go over to the Australian Space Agency and really interact with that emerging sector there. So I think similar things like that, where you're given opportunities to come and visit these hubs of research and activity, but maybe also more opportunities for researchers to go out and do outreach in communities too. I do outreach at the University of Adelaide, but I don't go anywhere. So the students come to me, but maybe it would be a good opportunity to have kind of, I don't know, researchers in residence or something where, yeah, you get a bit more exposure to what's happening even if you're living in rural. Yeah.
Will, what about you?
Yeah, I mean, this is something, I mean, personally, I grew up in the city of Perth, so I can't speak to everyone, but I have done lots of outreach research. We've traveled, I've been part of the Equus and Quantum
The
road
road
trip.
show?
Yeah, the road trip, which goes around to various communities. And so I will say that this is something that lots of people think about a lot. And just about everyone, we have a really large and great outreach committee from research. So not only researchers are thinking about this, but teachers as well. All the teachers we met on the road trip are really, really great. So, if you are in one of those communities, I think the first path is to speak to your teacher. And researchers, for researchers, it's about building that network and getting back in touch with teachers in remote communities and seeing what we can provide. Because it's things like this conversation we're having right now is something that's very accessible, right? So I think there's a lot.
I think those networks are really important. And one other thing we might want to add is that a lot of the companies like IBM and Google and Q Control have got amazing resources on online, which you can access and actually play with toy quantum computers and learn how to program them. And they've got online tutorials and things like that. So that might be a good place to go as well. Look, we've run out of time now. We're a bit 5 minutes over time. So I want to say thanks to Lucy and Will for that. I've learned a lot as well. It's been great to meet you and talk about your careers so far. But let's go back and hear from Natasha as she wraps it up for us.
Thank you very much, Cathy, for your time today, for facilitating today's session. And thank you to Will and Lucy for also sharing your stories with us. It was fascinating to hear about your career journey so far. I was really struck by how you all followed your intellectual curiosity and ended up as physicists after considering other careers like teaching, medicine, and engineering that were perhaps more visible. So thank you for being here today to make physics careers a bit more visible to that next generation. I also want to thank everyone in the classrooms and offices who have joined us today, and a special thank you to the participants who sent in questions for our speakers. I particularly loved the question and Will's answer on how do you choose what to pursue academically if you have too many interests to study them all. You're in good company, as many scientists have diverse interests and accomplishments. Being a curious person with a lot of different interests and talents is a really wonderful problem to have. So we hope this session has left you with a better idea of some of the different careers that you can pursue in quantum physics as we celebrate 100 years of quantum science this year. So we do have another Shape Your Future session coming up on the 10th of April. That one, we will explore careers on using Earth's natural resources from soil to industry. So we hope to see you there. Thank you for joining us, and bye.